Both of breadth first search and depth first search are general techniques for traversing a graph. So they're both going to visit each vertex and each edge of our graph exactly once, marking vertices and edges initially as unexplored, and then later marking vertices as having been visited, and edges as being either discovery edges or non-discovery edges. In depth first search, non-discovery edges are marked as back edges. In breadth first search, non-discovery edges are marked as cross edges. We'll talk about why we call them these two different things in a moment. But both depth first search and breadth first search can use this resulting edge labeling in order to compute a spanning forest of our graph. So this is that the discovery edges induce one spanning tree per connected component. So one spanning tree per connected component. So this gives us a spanning forest because we have multiple spanning trees. If we have only one connected component, then we have just one spanning tree, and our graph is connected because we have only one connected component. If we have multiple connected components, then our graph isn't connected, but we at least know what each of those connected components are. So this gives us connectivity information as well. And both of them run in total linear time. So this is big O of n plus m, how many vertices plus how many edges. And we can extend both of them in order to solve some other common graph problems, like finding a path between vertices, finding a simple cycle if there is one. The existence of a non-discovery edge immediately gives that our graph has a cycle. Now, when it comes to finding a path, both of them can find a path, but BFS exclusively is able to guarantee that we can find a shortest path, shortest in this case in terms of the number of edges. We'll see other ways to find a shortest path if edges have weights associated with them. But BFS will give us a path that has the least number of edges. DFS might, but it's not guaranteed to do this. Certainly there are instances where DFS maybe would find us a very long path. Now, both of these algorithms can be implemented in another way than what I had shown by using a data structure to keep track of which vertex will be visited next. And in this way, we could implement, let's say, DFS. That doesn't look like a D. DFS, we can implement using a stack. And we kind of did this. We mimicked this with the recursion stack. And this stack is just keeping track of which vertex to visit next. So we push a vertex onto the stack that we say we're going to visit this one next, and then we pop a vertex off of the stack, and that's the vertex that we do visit. And breadth first search can be implemented using a queue. And again, we mimicked this using just a list. This was our layering scheme. Now, why do we call the non-discovery edges differently in depth first search or breadth first search? With depth first search, we call these as back edges because in the tree of discovery edges, a back edge indicates that we're going from a vertex to an ancestor of our tree. So a tree of discovery edges would be that tree which is given by only these edges in blue. So if we were to draw this so that the root of our tree is up above, here we have vertex A to vertex B to C, which goes to D and E, and D has child F. So this is our tree induced by discovery edges. A back edge with DFS means that we're going back to an ancestor. So for example, from D to A, this is going to some ancestor. A is an ancestor of D in this tree. Whereas with breadth first search, we're not exactly constructing our tree that way. A non-discovery edge here, to go back in this way would be impossible when we're using breadth first search, because breadth first search will always visit all those vertices which are within one hop, one edge away from the previous layer. So if we had something like this, where F is reachable from A, where D is reachable from A using only one edge, then we would have visited D next if we were using breadth first search, and this is exactly what we see here. We use all of those edges which are one hop away from A first, everything which is incident on A first, so we get to all of those edges, all of those vertices which are one hop away from A, from vertex A. So a non-discovery edge here means that we have some edge which goes, yes, it goes back to a vertex we've already encountered, but where this edge exists in our spanning tree induced by discovery edges is this edge goes either across within the same level of our spanning tree, or it goes just to the next level. So this is why we call them back edge. This is going back to an ancestor of our tree. And in cross edges case, this is we're going to a vertex that belongs to the same level or just to the very next level, but we don't kind of skip around anything more than that. Now, breadth first search and depth first search, they both solve a variety of graph problems. We get a spanning tree for each connected component, and that spanning tree is induced by discovery edges. So this gives us a spanning forest of our original graph. One connected component means we've got a connected graph. Multiple means that our graph is not connected, but we can still find all connected components. We can find a path between vertices. We can find if there's a cycle in our graph. But there are some problems where either depth first search or breadth first search is uniquely suitable for. So for example, finding a shortest path between vertices. If we want to find a path that uses the least number of edges, then we would have to use breadth first search. And there are other problems, and you'll see in the next video, which are uniquely suitable for depth first search to be used, and this is if we want to find a biconnected component. So much like we have for trees, for example, different ways to traverse a tree, pre-order, post-order, in-order, level order traversal, just kind of depends on what problem we're working on, which traversal we would want to use. Similarly for graphs, we have these two different traversals, depth first search or breadth first search, and while both of them can solve a variety of problems, there are some instances where very specifically we would want to use one of them, or we'd only be able to use one of them in order to solve our problem.